Welcome Calc 3 fans. In this video we're going to be discussing a couple tests for convergence and divergence of series. The first test is called simply the test for divergence, and then we'll also discuss a test called the integral test. We'll finish this video with a short summary of where we are. Okay, here's the test for divergence. Recall that we saw that an infinite series is convergent if its sequence of partial sums converges. Well, in order for that sequence to converge, you can imagine that the sequence will not converge, I'll say, if the thing that you're adding is not going to zero. So the intuition here is that if the ith term in the partial sum doesn't go to zero as I gets large, then there's no way for the partial sum to go to zero. And this is precisely what the test for divergence says. So here's the test for divergence. Consider the series the sum n equals 1 to infinity of a sub n. If a sub n doesn't go to zero as n goes to infinity, then the series is automatically divergent. So here's an example of the use of the test for divergence. Go ahead and consider the series sum equals n, sum from 1 to infinity of n over n plus 1. So observe that the nth term in the series does not go to zero as n goes to infinity. Okay, in other words, the limit as n goes to infinity of n over n plus 1 is equal to 1. So by the test for divergence, this series is divergent. Okay, and the intuition here is that when you get way out here in the series, you'll be adding up things that look like about 1 plus 1 plus 1 forever, and there's no way that that sum can close in on a number. Now, I want to point out that a negative result in the test for divergence doesn't tell us anything at all. In other words, if a sub n does go to zero, the series could diverge or converge depending on a number of things. So a negative resultant theorem, that is a sub n goes to zero as n goes to infinity, doesn't tell us anything. And to see an example of this, let's go ahead and have a look at the harmonic series. So, of course, a harmonic series is the sum from 1 to infinity of 1 over n, so 1 plus 1 half plus 1/3 and 1/4 and so forth. Now, this series does have an nth term that goes to 0. That is, the limit as n goes to infinity of 1 over n is 0. However, we saw before that this series diverges. Okay, so again, having an nth term that goes to 0 doesn't tell us anything. The series could converge or diverge. You can think of this test for divergence as to have any hope of converging, the nth term in the series has to go to 0 as n goes to infinity. Test for divergence. Okay, go ahead and talk about the second test in this video called the integral test. Here's the motivation. The motivation is that an infinite series is a little bit like an improper integral. So we can consider, for example, the sum n equals 1 to infinity of 1 over n squared. So, of course, this series is 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, and so forth. And we can think about it as an approximation of an improper integral. So here's sort of a Riemann sum representation of that infinite sum. We have this first rectangle that has area 1. We have the second rectangle that has area 1 over 2 squared, and then 1 over 3 squared, and so on and so forth. So it looks like geometrically, at least, we can relate this infinite sum to the improper integral of 1 over x squared on the interval from 1 to infinity. And here's that relationship. So the relationship is that the infinite sum, the series, is less than or equal to 1 plus the improper integral. And in order to see that, just remember that the improper integral would be the area under the curve on the interval from 1 off to infinity. Okay, so certainly there's some gaps here, and these gaps are where we find the inequality. Now, one thing we know is that this improper integral converges. It has a value of 1. So this was a result from Math 162. So therefore, we can say that the sum from 1 to infinity of 1 over n squared is is strictly less than 2. Okay, in fact, it's pretty cool. Euler actually found that the sum of 1 over n squared from 1 to infinity is equal to pi squared over 6, which is roughly 1 4/10. In any case, definitely less than 2, definitely convergent. Okay, so the idea here, and this is sort of the intuition behind the integral test, is that when you can cook up a improper integral that resembles our infinite series, the infinite series and the improper integral converge and diverge together. So that's the integral test. Suppose that f is a continuous positive decreasing function on 1 to infinity, and suppose that a sub n is f evaluated at those integer spots n. Then, whenever the improper integral of f converges, the infinite sum does too, and whenever the improper integral diverges, the infinite sum does too. Okay, so the strategy here is that if you're faced with an infinite sum where the sum a sub n looks like something that you can take an integral of, try using the integral test. And you should remember that you should always check first, right? Continuous, positive, and decreasing. Okay, so an example of using the integral test. Here's the first one. Let's test this series for convergence with the integral test. So we sort of know that this series converges already. We checked it out using that inequality, but let's go ahead and have a look at it with the integral test. So here we would define our function f of x to be 1 over x squared. Okay, so we'll take our function f of x to be 1 over x squared, and then we have to ask ourselves, is this function continuous on 1 to infinity? And of course it is. It's positive on 1 to infinity, yes. And it's decreasing. It's quick to see that it's decreasing because the derivative is negative 2 over x cubed, which is definitely negative, not positive. Okay, so the derivative here, negative 2 over x cubed, is definitely negative on 1 to infinity, so decreasing. So the upshot here is that whatever the improper integral and the series do, they do it together, so they converge or diverge together. Okay, so the series and the improper integral, again, converge or diverge together. So we know what happens to the improper integral because we're experts in Calc 2, so we'll work that out really quick. So we know that this integral from 1 to infinity of 1 over x squared can be expressed as a limit of a proper integral. We know how to find antiderivative here. We know how to use fundamental theorem of calculus. And we know how to take the limit as n goes to infinity. We get 1, so we know that this integral converges. So here's the punchline. By the integral test, the sum from 1 to infinity of 1 over n squared also converges. Okay, here's another example. Let's go ahead and test this series for convergence, the sum from 1 to infinity of 1 over the quantity n squared plus 1. Okay, so here again, we see something that looks like something we can integrate. So we'll go ahead and define our f carefully, check that the integral test applies, and then use the improper integral to say something about the series. So we set f of x to be 1 over x squared plus 1, and then on the interval from 1 to infinity, we ask ourselves, is it continuous? Yes. Is it positive? Yes. And is it decreasing? It is decreasing too, and again, you can check that just with the derivative. So there's the derivative, which is negative on 1 to infinity. The integral test applies, and we know something about the improper integral of this function. So it turns out that the integral from 1 to infinity of 1 over x squared plus 1 can be expressed as the limit as t goes to infinity of the arctangent of x evaluated between 1 and infinity. Now, of course, that limit as t goes to infinity of arctan t turns out to be pi over 2. And of course, arctan of 1 is pi over 4. So we end up with pi over 2 minus pi over 4, which is pi over 4. But the big deal here is that this integral converges. So by the integral test, our series does too. Now, one final example here. Let's go ahead and have a look at the series 1 over n to the p power. Now, we should recognize this series in the special case when p is equal to 1. In the case where p equals 1, we know that this is a harmonic series. Of course, in the case where p is a number that is negative, we have an nth term that doesn't approach 0 as n goes to infinity. So that series is definitely divergent. So we'll go ahead and think about this series for p positive and p not equal to 1, and take the function f of x to be 1 over x to the p. So here's our function f of x equals 1 over x to the p. Of course, this function is continuous, it's positive, and it does turn out to be decreasing. Just look at the derivative. So the integral test says that the series and the improper integral converge or diverge together. Now, we saw in Math 162 and Calc 2 that this improper integral converges when p is greater than 1 and diverges when p is between 0 and 1. So that's what the series does too. So here's our series 1 over n to the p, which converges when the p is a number that's greater than 1 and diverges otherwise. So again, one special case of this is a harmonic series, which we know is divergent. That fits in here. A second special case is the case we looked at earlier, when p is equal to 2. That is the series of 1 over n squared, which we saw as convergent. That fits here too. Okay, just as a summary, this is a special series called the p series, and the p series is convergent for p greater than 1 and divergent when p is less than or equal to 1. Okay, so to sort of wrap up where we are at this point, there are several series that we know convergence of, and here are those series. One of those series is the geometric series. The geometric series can be expressed as a times r to the n, where n goes from 0 to infinity. This is one of the few series that we can actually find the sum of. This series is convergent when the ratio r in absolute value is strictly less than 1, and in that case, it converges to a over 1 minus r. The harmonic series always diverges. Of course, a harmonic series is a special case of the p series where p is equal to 1, and we know about convergence of the p series too. The p series is convergent when p is greater than 1, strictly greater than 1, and divergent when p is less than or equal to 1. Okay, hope you've enjoyed this video discussing a couple series tests as well as a summary of some series for which we know their convergence. Thanks for your attention, and we'll see you next time.